Well, welcome everybody to Conversations on Critical Operations. And today we're going to be talking to Dr. Roger Boulton. He is a professor of enology and of chemical engineering at University of California, Davis. Good morning, Roger.
Good morning, Nick. How are you?
Real good, thanks.
Thanks.
We're also talking to John Matranga. He is OSIsoft's Director of Business Incubation and Acceleration. Good morning, John.
Good morning, Nick. Great to be here.
Great. And great to have you. And great to have any of you viewing us on YouTube. If you want to ask questions, just use the chat window within YouTube, and we'll get to them right away. So, John, Roger, can you go ahead and give us a brief introduction to the university, to the winery at the university, and to your work at the university?
Certainly. So the department is a mixture of people in plant background in viticulture and wine chemistry and science and engineering and enology. So it's a joint interdisciplinary department. It's very old, 140 plus years. It's in the College of Agriculture, but it has overlap with College of Engineering. And within that program, have undergraduate masters and PhDs, obviously, but the programs would be called viticulture enology at the master's and bachelor level, but whatever graduate group in the PhD category. We operate two vineyards, two or three vineyards actually, two in Napa Valley and one in Davis, and we operate a teaching and research winery at UC Davis. And it's the teaching research winery, which is perhaps part of the topic of what we'll talk about today. So that's the academic setting. There are two other people now in engineering background that have joint appointments in chemical engineering. But it's a very interdisciplinary department where we could go from talking about the genetics of resistance to insect attack in grape leaves or roots in a faculty meeting next to a person who's talking about real-time simulation of fermentations and a person who's doing volatile aroma compounds and receptor perception on sensory. So it's a very, very interesting group of both academically and teaching curriculum, but also in research.
Okay. So now what kind of opportunities are there for using real-time data to improve what you're doing with energy management and water management?
Enormous, actually, because the thing is, this is now a process engineering, I suppose, element imposed onto a seasonal cycle and seasonal variation. So timing of when you start to do things on a 2 to 3 month harvest period is so there's no start date until you actually probably a day or two away. So it's not like, well, let's start this on the 1st of September. It's when the grapes are ready for this first lot of fermentations. And that will vary by season. The water requirements to actually operate will vary by season. The energy loads will vary by day and by hour in price. So there's a lot of things to manage which are not just average values, but actually more likely deviations from the values. So it's the robustness to measure the deviations, the ability to actually plan and predict what if kind of a scenario, to tie that both to resources and to value, and yet still manage limited resources such as energy and water. So it's a mix of all of that together, which is quite different from running a refinery or a power plant. Quite different from many other process industries, which it's most aligned to things like milk and dairy, but that, while it's somewhat seasonal, is every day of the year. Somewhat like brewing and spirits production, which again is batch driven, but may have more production at some point than other. Grapes effectively have in the world of wine, a 3-month lifetime between harvest and when they've finished fermentations. And that's enormous intensity of effort. All of the resources that you would expect to have for, say, a brewery are going to be there for a winery, except you're only going to use them a quarter of the year. And that, again, sets this unusual economic perspective and unusual seasonal, variable environment.
Mm-hmm. Okay, and now, like a lot of folks in manufacturing, you're getting real-time data from a whole variety of sources, right? And one of the issues is looking at them all, getting them all into the one place so that you can visualize them and also do calculations. Is that right? Can you describe some of that?
Sure. The best example of that would be fermentations. So the fermentation of red wines would be approximately 2 weeks. So the thinking that you're actually going to start something and it's going to go on for 2 weeks before it's finished, now you actually want to know a lot about how well it's going by day 2 or 3, and you would like to know a bit more about whether it's on track that what you would expect, or it seems to be going slower than expected. These are things which aren't yet how good is the wine when it's finished. These are things of efficiency of delivery to that final chemistry matrix. So that's for many years, people would simply do hand sampling of a tank, run the density, plot the density, or maybe write the numbers on a table or a graph if you wanted. But that would be the extent of whether things are going well and it looks like it's okay at this point. Now we would do that automatically, so that if you had 100 or 200 fermenters, that's not a problem. It's simply hook them up and where is that curve. Then it's, oh, well, I want to monitor them, and these are all slightly different. They maybe have different yeast strains. They might be at different temperatures. They might have different nutrient content, and their curves will be slightly different. But I want to be able to pick that up and model it. And the advantage of the modeling now is I want to see what it's going to do the next 12, 24, and 48 hours before it happens. And that's not just a smoothing prediction algorithm. That's a more rigorous analytical mathematical model that would include the things that have developed the history of the curve to date. So that modeling piece is, can you get the measurements? Can you pull them in one place? Can you do the modeling? Can you do the prediction? And here are the choices, and what choices do you want to make? And can you implement those choices? And so that's like a feedback control system with running very, very slowly. But because it's running so slowly, you've got to be very careful it hasn't gone off track, because it's going to be difficult to try and change its trajectory further and further down the road. So, and the other point is the value of wine compared to beer or spirits or other products. It's a multiple, 2 or 3 times. So per litre, something goes wrong, the losses per litre become staggering because of the value of the product you're dealing with. It's perishable, things can go wrong, and you're trying to make sure that it's delivered. The challenge of a winemaker is to deliver the grape chemistry into a finished wine mixture as well as they can. So it's, I would say, the single distinguishing feature from a normal process industry is fermentation monitoring and modeling and prediction. And because the prediction piece is the cooling load, and the cooling load is refrigeration, and refrigeration is electricity for compressors and cooling towers. And so now you've got a seasonal variation again on how the refrigeration system runs. Now you've got a load which is varying by time and temperature, but overlapping. So you might have 100 fermentations all in progress, but they're not all started at the same time, and they're not going to finish at the same time. They're often started 1 or 2 days apart. So there's this overlapping load curve, and now we want to turn the refrigeration capacity on, and we want to know what time of day it is, because we're going to pay different rates for both kilowatt hours in energy, but also
you're doing the thermal. You do a lot of tricks to the trade, the same everybody else in manufacturing does with thermal. Yeah,
that's right. But
yeah, I'm sorry, go ahead.
In a traditional industry, the concept of time of day billing and demand charges are virtually unknown. Most people think of getting a power bill and paying the power bill, a bit like we would in a house. We're not really looking at what did you use and when did you use it, but in this setting. So that's what's changed the landscape of why do you need these measurements, and why am I've got this power bill? It's hard to understand that I've used this much and this is how much it costs. So there's that element of simply quantifying the economics on a variable cost structure, where you don't have much option which days you're going to play, and you've got fermentations which are going to go on for 2 or 3 weeks. You've got to be a little better at understanding what the demands are going to be to anticipate those loads and make adjustments. And we can come back to the adjustments later.
Mm-hmm. Okay. And when you're also dealing with water management, and you're doing some interesting, fascinating stuff with water, right?
Sure. So when we built the winery at school, we had the opportunity to build into it a number of design features which essentially today's world would be what people talk about as net zero. In those days, again, this is a decade ago, we called them self-sustainable. So we wanted a winery which didn't use anybody else's water, and we wanted a winery that didn't use anyone else's electricity. And because it was a relatively small facility, that was a little easier to accomplish, but conceptually it was so counter to normal thinking that it was almost a point of ridicule. Today the question is, how did you do that and how did you build that? And this is in a dry place in California that gets, I think, 18 inches on average rainfall. How do you capture rainfall and filter it to reverse osmosis standards, what we call water for injection standards in the pharma world? High purity water that doesn't have microbes and doesn't need chemistry. And how can you use that water to clean a tank or a barrel, capture it, refilter it, and use it again? And so the concepts now are how to use water multiple times. Now you don't need nearly as much as you would have. If you'd had a waste facility, a wastewater treatment facility, now that would be considerably smaller. And so often the economic ramifications aren't the cost of water. It's the size of water processing and handling facilities if you use it once versus could you use it twice. And then when you realize putting in the piping and the collection systems to capture it for the second time, those all become the same things for the third and the fourth and the fifth time. So the winery was designed to use water 5 times. And because we were not quite finished with that feature yet, that's the objective. That lets you operate even 2 to 1, lets us operate in a very dry area on rainfall only from roof catchment, sterile filtration, to produce high purity water to wash tanks from wineries. And the corresponding energy one was everybody would have had solar panels. That was good, you could cover the roof. But we wanted batteries, or we wanted off-peak storage capabilities that let us operate in a mode which didn't depend on being on the grid. And so those 2 features are embedded in this building. Even though most people come to see the winery and the research facilities, it's like an outer shell that some people are interested in, and some people don't even see it, but it's there.
Okay. Now, you said that there was resistance to the point of derision, or I'm sorry, I've forgotten your phrase. But...
No, just people were saying, why would you do that? That was the skepticism was, you don't need to do that. And the answer is, well, if you understood the world's environment and climate conditions and ice cap melting, the question, we should have been doing this 50 years ago, self included, my career have not done too much about that except the last 10 years. And the answer is, I've got a lot of time to make up for. So this was an urgent thing to do in my world, but it was not yet an important thing to do in some other people's world. And then you realize that it's sort of a threat to their picture of the world when you say a facility would have to operate on its own rainwater and maybe use water 2 or 3 times. That's hard for many people to comprehend as a normal thing 10 years from now.
Yeah. Okay, good. Well, that's fascinating. So what kind of things are holding more folks back from doing this type of thing? What do you think?
I think it's 2 things. One, I'll say in the business world, and we could define what I mean by that, but I think people who are not winemakers, who basically manage the wine business of a winery, take the sales and marketing people out of it and talk about the actual winery manager, they I don't think see the urgency or the threat to their business of not having enough water. And I don't think they see the threat to their business of not having energy on a given day as being a potential risk that may be 20% of their income in a given year. It's not quantified that way. So they don't see that as a loss in sales or production, and they don't have an objective function to look at an investment against that in traditional return on investment kind of calculations. Now, what's the cost of the problem? What are their solutions? What do they cost? And what's the payback? If you don't see the threat or the risk, then you don't have the value function. Now you can't do the calculation. So now there's nothing to discuss because you weren't even discussing what you were going to invest in because it wasn't a problem. So these are what I call invisible problems. And you can think of most risk as an invisible problem. The question is, when does a management group recognize the risk? And when do they have, I'll say, financial tools or business management tools that let them evaluate the risk for an investment? And it may be a staged investment. It may not all be at once. But what would be the rollout to prevent, say, some probability of a risk occurring from occurring? Now, we do that with fire insurance. We do it with flood in California. We do it with earthquake insurance. But we would have crop insurance for rain and frost and so forth. But in operating a winery, we don't have what I would call power outage risk or water shortage risk. And those two risks are probably going to determine, I would say, the economic viability of probably half the industry in the next decade. So they're very real, it's just that it's not perceived as a problem yet. And then I think it's not only is it not perceived as a problem, it's not able to be quantified easily. And now we don't do investment analysis on risk management, we do it on perceived problems. So whether you don't have enough energy from your utility this harvest is one question. Whether there's times of day where you'll have a brownout and a voltage drop is another one. But in Northern California, certainly, and perhaps part of Central too, there are now days in the last 3 years where either fires or wind have allowed the utility to actually put people on notice to be shut down for 12 hours. Not just reduce your consumption. No, there will be no power. So this is now a power loss at an urgent time, and you're using a lot of energy and you don't have any alternative. But what's the probability of that and what's the risk of that? And I suggest that most people who are in the business world have trouble trying to quantify that. Otherwise, you can deny it, so forget the denialism. It's now that's real, but how big is it? And like most things, if you were skeptical about fire insurance on your house, do you have to wait for your house to burn down, or do you wait for someone else's house to burn down before I think I'm going to get some fire insurance? So that's a bit where we are, and climate affecting rainfall, growing populations on water demands. These are all things that are continuing to grow. They're not stable. They're not like we can plan on the next 10 years as being like the last 10. We're still increasing population. We're still building and developing. We're still growing communities. And the question is, there's only finite water. So at what point do you start to say the obligation in the future is you'll need to use it twice or much more efficiently if you're going to build a house or have an industry? That's going to probably come after the first droughts and shortages. Then the action will happen. What we were trying to do was prevent that by planning and design to never happen. And that's a different way of looking at a problem.
So Roger, you've seen hundreds of wineries around the world, and you've built up this winery at UC Davis, which is relatively small compared to a commercial winery. When people say, "Gee, that's you had it easy, right? You were working on a small scale." What's holding people back from doing this in the real world?
I would say a limited appreciation of the effective scale. And also, so a lot of people say, well, this doesn't translate, or is it directly proportional, or does it scale up? And the first thing I would have in that conversation is, no, 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 no. This is scaling down. So let me give you an example. The amount of water we use to wash a tank is really how much water per square meter of wall area. So we're using of water volume on an area. Now, when we do a water footprint, we would talk about litres of water per litre of wine produced. So if you make your litre of wine in small tanks, where there's a lot more wall area per litre than in a big tank, a large facility with large tanks is going to have a lower number, not because they're more efficient, they just have less area per litre to wash. So doing it at the small scale is actually the worst place to do it, because you have the highest amount of area per litre. You're going to need more water per litre than most other facilities that are bigger. And if you want to be 1-to-1, 1 litre of water per litre of wine, or in our case, less than 1 per litre of wine, you'll need to have a strategy of collection and refiltration, and you'll need to have a different strategy of chemical inputs or not. And you'll need to have different cleaning sanitation protocols for all that to happen. And that's sort of what we do. But the second is true with just energy loads and cooling losses. The refrigeration load of the fermentation is proportional to the volume. So kilowatt hours per litre is the same whether you're big or small. However, holding a wine in a tank at a certain temperature, particularly below ambient, now the heat gain, or the losses term, is proportional to area per volume. So in a small facility, you'll gain heat per litre much quicker than a big one. And so temperature maintenance is more difficult at the small scale than it is at the big scale. But both of those, if we went up 1,000-fold, so area per volume is scaled roughly by 1 over diameter. And so if we went up 1,000 times, we'd have 1,000 times volume, we'd have 100 times area, but it's 1 over that, so they have 1/10 of the area per litre. So a winery 1,000 times the volumes that we're dealing with should be using a tenth of the water, or even less. So I don't think that's understood well. It seems like a simple thing, but a lot of people haven't done the geometry calculation to realize where the water's going. And in the wine and brewing and milk world, it's primarily washing equipment, washing tanks, washing tankers. Surface area per volume is the metric. And so that's why a small facility is actually, it's not at a disadvantage. That's a reality. The question is, how do you adapt your technologies to be able to use the same water multiple times? That's only going to come from a small facility that gets that point. It's not going to come from a large place that doesn't feel its water footprint is very big, because on a litre per litre basis, it might be quite small.
So this lays out, you have some opportunities here that, you can kind of push out, and we'll get to that next year, right? Mm-hmm. With, I'll say, a competing situation, which we could have a catastrophic event this year, right? So yep. How do you see people balancing those two things, and what kind of things should they do?
I won't make a comment on the judgment, but I think if you were to look at the industry and the way that people talk about these things, there's a ways to go, I think, in the urgency of that and the reality of that. And it's interesting because farmers and viticulturists, grape growers, understand the sort of variability associated with frost and rain and hail and flood and drought. But when it comes to utilities in operating a winery facility, that doesn't normally transfer over. So it's back to, you would like to bank water, you would like to bank energy, and you would like to bank them when they're available, and you'd like to use them when they're needed. And the challenge comes, how big a bank account do you want? And if it was a bank account, it wouldn't matter, because the size of it is just numbers on the paper. If it takes up space, like water tanks or energy batteries or systems like that, now the question is, well, we don't have the space. So it's difficult to retrofit because typically we built facilities that didn't have the space to bring that in. Now the question is, where could you locate them to have that? But if you were to take a Google satellite vision of the winery at UC Davis, the first thing that becomes obvious is 10 water tanks. And these look like grain silos to most people, but they're actually water tanks. So in the conversation, people said, well, why didn't you, what's the point of having all these water tanks? You should have put them underground where no one would see them. The answer is, well, there's no learning from something you can't see. And the second is, a lot of people say, that's not enough water. And you actually want them to realize that that is enough water. That's more than enough water for 2 years. But so there's a reality of what space is needed that I think we have in an educational sense just to convey as an example, because a lot of people think that they're going to use, so if you were using, say, 5 litres of water per litre of wine, they're going to look at the storage tanks for their wines and barrels. They're going to say, we need 5 times that. The answer is yes. So but you can't have the conversation about why you would use water multiple times and capture it and reuse it until that, but you can't get to that unless you. So it's a how do you build a background to have the problem discussed in a way that leads to a solution? But essentially, it's storage systems. Now the question is knowing the difference between your availability and your use patterns. So you want to monitor what the loads are, you want to know what the generation is, you recognize that solar is each day and goes off each night, and yet you want to be able to use something almost continuously in the day. And the question is, how do you charge your batteries? How many batteries? What's the metrics on that system? And that's what the winery is an example of, for people to learn from and to be able to say, yes, that's possible. But the water one is now a bit tricky because we capture rainwater in December, January, February, which is the rainy season in Davis. And there's almost no rainfall until next November, December, almost none. So you need a 6 month holding pattern. And people say, well, you don't know how much water you'll need this harvest. And the answer is, well, I could go back 3 years and look at what the water consumption is. I can see when I introduced recapture and refiltration. I know what my annual usage is, and I might want 2 years rainwater. So people say, well, what happens in a drought year? And the answer is, well, I have enough water for 3 years. And I'm going to bank it for 3 years. Even if there's 2 years worth I don't even use this year, I need to bank that for the year when it's a drought and I don't have any rain, and I will still operate under that condition. Whereas most people say it's a failure. We can't operate. So that's I don't want to be as blunt as you're going to go lose your business, but we've got to work out how to bank that risk, how to work out that asset investment, how to work out how to manage that, and all of that gets down to capture and recovery, efficiency of recovery, chemistry of that recovered solution, trying to minimize using as much water as possible every way you can. But that also leads in the other side of it, which is discharging water with as least chemistry for the environment to have to interface with as possible. And that's the other objective in our cleaning chemistry and our winery. So these are all linked. Okay. How much water you get to actually operate, the usage of it, the recovery and efficiency of it, and the discharge chemistry are all, in my world, they're all the same thing.
So very much like you would in the design and the management, you would optimize for production and quality and safety. You're just bringing a couple of more variables into the equation here and closing the whole loop at a larger envelope. So sure. Does this have implications for other industries?
Yeah, of course. So the ones that are operating all year round that do the same kinds of things are breweries and the brewing stage of distillation in grain spirits or fruit, dairies, which are so food production facilities using stainless steel, which is batch prepared and needs to be washed. So that would be the category, and the answer is, well, that's almost every fruit and vegetable that's processed, whether it's fermented as juice or from carrots to peas to citrus to milk, cheese, all fermented products, all the way to pharma. Those are all in the same spectrum of stainless steel, fermentation, microbial risk and desire, and chemistry and batch. And now you've got to wash and get ready for the next one. So there's a similar, that's across the board. And then you get back to why are certain facilities located in certain places, and it may be because of preferential power, not only cost but availability and water access or not. But in the future, to get a permit, I would hope that in the future those will be questions that are asked at the permit stage, or of how much water are you going to do, where are you going to get it from, and what are you going to do with it? Not just will it meet the state standards of discharge. It's going to have to be where's it coming from and how are you going to operate it, which we didn't ask those questions before. We might have talked about them once the facility was built, but the answer is no, these have to be asked up front before the safety question and before the other aspects. Actually, is if you want to put something on this piece of land, please tell me where the energy and water is coming from, and tell me where the discharge will be, and tell me the activities you're going to do. They're going to change the chemistry.
Okay. Well, here's a question that's we didn't really talk about it, so I'm just kind of curious. Have you gotten any surprise benefits out of what you're doing? And you know, I'm putting you on the spot here, so let me, while you're thinking about that, let me show. It's a shame we're talking about vineyards. We haven't shown anybody these beautiful vineyards that you've got. So I'm just showing people some of the stuff there. You've got the Campus, the Kearney, the Oakville, and the Tyree vineyards. These are the ones you've been talking about, right?
Sure. And
absolutely beautiful.
And so again, this is a very small academic department of 14 people, 14 faculty, and it maintains and operates several vineyards for research projects, and it runs a winery as well for research projects as well as facilities for teaching. So a lot of people in plant science, for example, don't operate their own farm or plantation as a part of the plant science. They would do the theory, they would do lots of study, they might do research projects, but it's not part of their teaching program. The difference with viticulture enology is the viticulture vineyards are used for teaching, pruning, development, fruit composition, and all of these things. And equally, the winery is not just can you make wine and add yeast, but the entire process through to aging and bottling and sensory at the other end. So it's it's a very unique academic program, and it's a very unique, I'll say, industry. It's an industry-focused academic program, the likes of which there are very few in the United States.
Yeah, it is very interesting. In our lightning round at the end, I wanted to ask you some questions that I'm fascinated to hear about with, winemaking. But so yeah, putting you on the spot, but any surprise benefits? I think one of the most fascinating things about working with real-time data, people put a system in for one reason, and then they get an entirely different set of benefits just out of nowhere, just because they have better visualization, better analytics.
Probably the best one that I think was not an unexpected one, but so apart from the winery building, which was finished in 2010, we have an ancillary building which is for many of the unit operations of the water and energy, and that's referred to as the Jess Jackson Sustainable Winery Building. That building was built to exceed passive house standards. So I think it's the largest building built that is net zero in its own energy. It has panels which actually operate nighttime fans, and it has very high insulation, so it has no air conditioning. So this building essentially stays constant temperature in Davis, where it could be 100, 105 in the summer peak afternoon temperature. And at nighttime, we often have a delta breeze. We'll bring it down to maybe 60 Fahrenheit. That oscillation, which you see in a weather station, the big sinusoidal going up and down, that's pretty cool to think of the climate oscillation. But now to look at a building vibration of that, so the thermal vibration of the Jackson building is essentially a straight line. it varies by less than 2 degrees daily, where the outside temperature would vary by maybe 40 or 50 degrees. So that, as an example of a better building, just by measuring inside temperature and outside temperature and having designed it to be a very high passive building, that demonstration alone was picked up because we now can pull that into Pi. I had a student from Italy, a postdoc guy at the time, doing architecture of agriculture buildings. When the Jackson building was being built, he wanted to be here and he wanted to see everything they did. And he then starts teaching a course on agricultural building architecture at university in Italy, in Bologna. And he wanted to know, could he get the data for the Jackson building? And so he was using diurnal cycling of the outside temperature and inside temperature of the Jackson building to teach students in Italy how to build better passive buildings for agricultural buildings. And I'm going, what? This was not in the plan. This was not even in the thinking that this would be anything that it would ever be used for. But it indicates how it ripples and carries over into other fields. In this case, architectures and building. And that's an unexpected outcome, but we had the data. If we didn't have the temperature data streaming, he wouldn't have been able to do that. He wouldn't have been interested in doing that, and we wouldn't have been able to let him do that. And you say, well, this is just 2 temperature probes, one in a weather station and one in the building. Well, it's actually an array of 12 in the building. It doesn't matter. These are relatively simple things, and yet the understanding of the thermal dynamics of the lag and the attenuation between an environment and a building is profound. And there are very few examples of that even on the web today. So people learning building architecture, talking about building lead buildings, they want reference examples of this. And so I've had people from all over the world come to visit these facilities, not for winery research or teaching, but because of the advancement, I suppose, of the monitoring and efficiencies of the buildings themselves.
Yeah, I was actually able to pull it up on your main web page. You have the trend for the internal temperature. Anyway, very, very cool. So, so the other thing I wanted to ask, and you're using this in your curriculum in some way. Is that correct?
Yes. So, how can I say further? We use it in all of our research. For example, we monitor every fermentation. Different researchers set the conditions for those experiments, but they can log that and see that in a way that remotely, anywhere, they can share it with colleagues overseas. But this last year, with design teams in electrical computer engineering, which is a sort of a sister department with some faculty members that help us and work with us on different things, they actually developed a phone app that can now, standing in front of a fermenter, looking at a QR code or a 2D barcode, taking that image will pull down the fermentation curve as it's developing for density, temperature, and redox potential, and allows you to go back to a different database and pull the juice composition of that juice when it started. And then you can move to the next tank and do the same thing. So the feedback is immediate. It allows a student who might be going in to look at one of their fermentation tanks. I'll bet you that almost everybody that does that now will go back and look at 6 or 10 others just to see how they're all going. And there's spontaneous learning and questioning and discovery, all because that information was always being collected. It just wasn't very accessible. Now it's accessible. Now it'll be part of a question and answer ongoing part of every lab fermentations from now on.
Yeah. No, I mean, we see that all the time in our training. Obviously, when people are making use of their own data, it's ridiculously engaging.
Right.
So yeah, that resonates. That rings very true with what our experience is with using your own data, of course. So that's good to hear. John, you're familiar with? They're not the unique and being folks who have integrated this into curriculum. Is that right?
No, not at all. Yeah, so um, the academic program within OSIsoft has a strong outreach to make the experiential learning component of this real-time data front and center to students, right? And bring that alive. Roger talked about having the students be able to see the size of the tanks and understand that. Well, when you walk up to walk up to an environment and be able to see the cause and effect of things that you're doing in real time, that's really powerful, and then it just reinforces the theoretical things that you've already been learning along the way and makes those come to life for you. So we're really proud of
Mm-hmm.
that program.
Yeah. Well, that's one thing that real-time data has a way of doing. In many cases, we hear customers say that this facilitates conversations. It absolutely, it's. I mean, one of the truisms of most manufacturing is unless you've got a good handle on the truth, you spend the first 20 minutes of each meeting arguing about whose spreadsheet is right.
Yep.
So yeah, and it's nice when you don't have that. So okay, great. Well, let's see. I guess the only other question to ask is, are there any future uses that you see you being able to use real-time data for in your work?
Well, the classic would be right now with COVID and basically shut down, so the campus is closed. We could conduct fermentations in the winery with a limited skeleton crew, well protected, and the students online, instead of just doing Zoom sessions and presentations, would actually be looking online in real time at what they would normally be doing if they were in the winery. That's the first point. The second is that we could share that with every other institution in the world that wants to run wine fermentation studies, who may not even have a winery, but they could tap into that and use it, and we would share it because it's for everybody. So there are programs which don't have facilities that would learn from a facility, and that's available right now, and that's possible. And it goes further. You could transfer that into other languages and so forth, but most people understand the dynamics and the scales of what we're talking about, and there's probably 20 schools around the world that would love to have that ability, and we can do that and share that now. So that's the first one. The second would be, once we get up and running with the water system in a completed loop, we'll be having people chime in and look at what water we're using, what the chemistry of it is, how we're implementing and recovering that. There'll be a lot of other things to learn that will be able to be visible, and again, globally. This is we're not doing this for people who come to campus. The outside reach piece of it was always everybody in the world of wine, not just students. It's our own students, clearly, but the examples go internationally, and that's now available and that's possible. So this is a very small department. There are many universities with some very large departments, but very few of them have what I would call real-time laboratories as part of their undergraduate or graduate curriculum. And we're incredibly lucky to have that, and that's what we do.
Well, thank you so much for joining us. If there's anything that we haven't talked about, let me know. And in the meantime, I wanted to ask you just a bunch of real quick questions. What's the most common wildlife that strays onto a winery? I'm just kind of curious.
If you're in South Africa, it could be baboons coming out of a forest to steal the grapes. If you're in Australia, it could be an emu or a kangaroo that decided to sleep on the porch because it was cooler. I'm sure there's other examples, but it's.
Well, what's the oddest thing you ever had in? You're in the San Joaquin Valley, in UC Davis. What's the oddest thing you've ever strayed onto your property there?
That'd be a king snake, And so there was a king snake that came into one of the buildings, not the winery, but the adjacent academic building, and it worked its way up the wall behind the plaster. And I with two colleagues were coming out, and we saw this thing, and a big long black snake with some pretty markings. And I thought, boy, that's a snake. And then we sort of looked at it. Anyway, the irony was that, as you probably know, king snakes like to eat rattlesnakes. And one of the biggest concerns in vineyards is, and certainly dry areas, rattlesnakes. And so somebody said, "Oh, we've got to report this and get someone to come and catch it." And I said, in the natural world I come from, I'd like to have a king snake because that means there's no rattlesnakes.
That's great.
The other one, last one, is there's a vineyard. We're working on a project on Malbec with a student from Argentina, and his thesis work was on Malbec from different regions, and we were going to pick the grapes. And one of them was up in Lake County, and the vineyard was called Cougar Ridge. And we'd gone through this vineyard 2 or 3 times, different occasions, and we were going in to pick, and
is that the technical term, going in to pick?
Well, in our research world, we have to go and pick our own grapes often. Sometimes we'll get help, so we would drive up early in the morning to go to Lake County, to be there at 5 o'clock with sunrise, to be able to start picking, to get back to school, to get them crushed, to get them in the fermenter before we went home in the evening. A long day, but anyway. So Fernando said to me, "Well, this is Cougar Ridge. What's a cougar?" And I said, "Well, a cougar is like a mountain lion." And so he was then couldn't wait to see the vineyard manager to say, "Are there any cougars on Cougar?" And the guy says, "Yeah, we see them." And Fernando was just about melted. he was like, so this is wildlife, and we're encroaching in their territory. The question is, we'd expect to see them. The winery bit is now, it's often either for water or for heat or shade or protection. It's natural that an animal would look at a site like that and say, "This would be a nice place to have a sleep this afternoon." So those are probably the two or three silliest ones I can think of. But anyway.
Okay. Well, what's the? Are there any calculations or just correlations between variables that you found absolutely fascinating? So I know, when we were talking to one customer, they were making carbonated beverages, and they didn't recognize. Until they did some XY plots, they didn't recognize that the intensity of the sun had a huge impact on the amount on the difficulty of carbonating their beverage.
Yep.
And so they ended up having to put up panels to block the sun and whatnot. Any correlations like that, or calculations that you ended up doing?
In my own experience, dozens and dozens. So my background is chemical engineering, and I had taken courses in microbiology and fermentations and in Australia before I came. So I had a very interesting physical chemistry, chemical engineering, fermentation collection to go into an industry where there were essentially no engineering people at all. Certainly not a lot of impact of what I would call chemical engineering. So there were lots of times when I would sit and do calculations of things that people hadn't thought about. Perhaps the most interesting one is the scale-up effect in a red fermentation. So a red fermentation would be where we take the grapes, crush them, get the juice out, but we put the skins, with the pigment in the skins, in with the juice. And as we ferment, we're mixing that combination in what we call a pump over. We're trying to extract the pigments and phenolics out of the skin as the fermentation is going on. So there's a physical fluid extraction equilibrium going on, in addition to the yeast fermentation converting sugar to alcohol and putting off CO2 bubbles. And there's a change in solvent properties. So it's a very interesting mixture petitioning problem. The challenge is that in a small tank, so roughly of the volume or the height of a red fermentation, roughly a third of that volume is the skin cap. Because once the skins are almost the same density as juice, so before fermentation begins, they just sit there like pulp, and there's no settling or aggregation. They're neutrally buoyant. But once fermentation begins, you actually get bubbles floating them, and they actually begin to form the skin, what we call the skin cap. Now, if it's if the height of that fermenter is say 9 feet, and the top third from 6 to 9 is the skin cap, it's a 3 feet skin cap, and the weight of the skin cap is the compression, because the bubbles are floating it from the bottom. So the squeezing and the channeling is directed to 3 feet. But if I took the very same grapes 100 times as much, put them in a big tank that was now, say, let's keep it simple, 27 feet high, now the skin cap would be 9 feet. Now the weight of the skin cap will be 3 times greater. Now the compression on the skin cap is very different. Now the channeling is different. Now the heat buildup is different, but they're the same grapes. And so that effect of scale on permeation and skin cap behavior, on temperature buildup, because often mixing the colder wine onto the skin cap is what controls the temperature of the skin cap, and we don't want that to get too hot. That scale effect is something that I don't think most people in the world of wine has ever thought a lot about, because they typically had one size fermenter. And
wow.
And then you go back and say, well, how do different people do things? And there are places in Republic of Georgia where these would be in earthen urns in the ground called qvevri, and we'd put the grapes in there and it would sit there and it would ferment away. But it's just they're small, so it doesn't build up that much heat because they're small. They're losing it quickly to the surroundings. You could go to other places where people have concrete tanks. You could go to places where they have cylinders, rotary tanks, and you could go to places where they've got open top tanks, and you've got places where they've closed tanks. And so I've often said, if you arrived, so 3 rockets I think are on their way to Mars, if they find anybody and the people come back, when the Martian arrives and goes to visit a winery, he's going to say, gee, that's interesting, what's this thing? And the guy's going to say, oh, it's a fermenter. And I said, well, let's go and look at it. He would go to 10 different wineries and he would see 10 different fermenters. And now I'm giving a Martian good intelligence to think that what that says is it doesn't matter. So if people do something 10 different ways, what it says to me in the empirical world is it doesn't matter. It's not that critical. Size might be, but not shape or geometry of things that you're doing. And so otherwise there would be some consolidation of what is the best. After a few thousand years, you think we would have worked out what would be the right ratios or the right stoichiometry. And the answer is the fact that it's so variable and we can intervene with mechanical things, it's a fuzzy area.
Okay.
The other side, so that is in a world where you would say, no, it should be more precise. We can calculate that exactly. And the answer is maybe it doesn't matter a lot. So people will talk about mixing and whether we get better extraction and everything else. I'll go back to their point. If there was one way of doing it that was significantly better than all the others, people would have moved and migrated to that because that would have been viewed as the best color or the best extraction or the best balance of extraction. And there isn't one.
Okay, interesting. Well, one last thing then. Is there a trade paper or publication that you would recommend if people were really interested in learning more? Something you think would be a good entree?
There's there's one called Practical Vineyard and Winery. There's one called Wine Business Monthly. There's ones in different areas in the world that have different sort of industry magazines and often an annual technical issue. And then it gets into published and refereed papers. And so there's an American Society for Enology and Viticulture, and they have a journal, which is the American Journal of Enology and Viticulture. There are several grape and wine research journals in the world, maybe half a dozen. But those, so it's interdisciplinary. It's not like it's all in. It's not as clear cut as many other disciplines are. It's spread out, if that makes sense.
Yeah. Well, it's been fascinating what you've told us about it. Thanks for joining us. Is there anything we forgot to talk to you about that would be worth?
Yeah, probably cleaning chemistry. So how can I go backwards? So today, if you you wanted to make something really clean, there's two issues. The general way that people clean tanks for brewing and fermentation and pharma, if you said to them, what's the major problem, they'll talk about biofilms. So you've killed all the pathogens that you were worried about. Now, in the wine world, we don't have pathogens that survive at this pH in alcohol. So it's not a pathogen problem in wine. It's just a spoilage bacteria or spoilage yeast problem. But the question comes is, you can kill them with all sorts of chemistry. The real technique and question now is, well, but you've got a biofilm left behind. What's a biofilm? So in the engineering world, a long time ago, I started looking at what were the properties of stainless steel surfaces in charge. Now, most things have what we call an isoelectric point when we're talking about solutes, proteins, for example. It's a point at which they're not positive and negative, or they've got equal numbers of them. They're essentially neutral. But otherwise, at lower pHs, they're positive, and higher pHs, they're negative. So now if you've got a surface that has a surface charge, depending on the pH of that condition, whether there's those certain molecules want to form a monolayer or a boundary layer on the surface. And if you wash them with a pH which is complementing that, they're going to stay there. So you can wash them and you can kill all the bugs, but you're not going to peel off the molecular layer, which is the basis of which other solutes get trapped, organisms begin to get growth and cultures, and you get the biofilm. And so the starting condition, that is the physics of charge of surfaces, stainless steel, and the pH of the cleaning solutions. Standard practices would be to use a high pH caustic condition to clean the surface and to kill everything. In the old days, people would have used chlorine. Some people would have used hypochlorite and other variations of it. But if you're now looking at the environment's going to be, where does the chlorine go? Where does the chlorine dioxide go? Where's the sodium from your caustic? So you can do these things, but now what's the output to the environment of that? And so building this winery led to that consideration that we didn't want to use sodium salts, because they're not particularly good for clay and ground, which is going to swell and expand and go to dust if you keep on putting sodium salts onto clay soils, with much of the vineyards are clay soils. So the question is, well, stop putting the water on the vineyard because it causes the degradation of the clay. And the answer is no, it's the sodium in the discharge water from the cleaning of the stainless which is actually causing the problem. So many years ago, we put a proposal forward to actually do potassium-based high pH, low pH inorganics, so they have no contribution in BOD or COD in wastewater ponds, equally matched, so if you mix the two of them together, they're pH 7 neutral. But by maintaining certain pHs, you had a condition where the stainless steel could be made to be positive, and most of the molecules around in the cleaning that you're trying to sweep off that film are positive. You would actually be able to remove them. But if you set up a pH condition of cleaning where they're negative stainless and those things are positive, now they're actually going to form a biolayer. So we have a cleaning protocol at school which is potassium bisulfate for pH 2.5, potassium hydroxide at pH 11.5, what we say fractions of a gram per litre, fractions of a % of content. And we have a cleaning protocol where you would use the low pH first, because you actually want to have the stainless in a positive state to drive off the things that were positive that stuck on it. Because in general conditions of wine and winemaking, it was negative. So knowing the engineering of the surface materials for isoelectric, knowing molecule charges with pH, understanding laminar absorption of a monolayer is the precursor for biofilm, I believe we're running a cleaning system which is superior to anything in current practice. And then the question comes, well, the pH just doesn't kill the bugs, so what would you use? And you would use hydrogen peroxide. So we would use peroxide at 1%, which is a third of what you could do if you went to the pharmacy and bought a little brown bottle of peroxide. Not concentrated, very dilute. That can kill E. coli in a matter of 20 minutes, 5-decade reduction. It'll decompose to oxygen and water, very clean. And when we go to filter it, there's no chemistry except for the 2 buffers we used, which if we recover them on membranes, allow us to use those buffer solutions again. So not only are we using water multiple times, we'll be using chemistry of the buffers of the cleaning multiple times, and we'll be maintaining the conditions at which those occur much more precisely. And when we come to discharge them, it'll be potassium sulfate. So, that's an environmental answer of an engineering cleaning physics problem, of a microbial cleaning pathogen concern, and multiple uses of water. Does that make sense?
Mm-hmm.
All wrapped.
No, it makes sense. It makes sense. And I imagine the role real-time data played in that was
Yes.
fairly important.
Yes.
Yeah.
Yes.
Yeah.
So we could tell the difference between those solutions based on their pH, their conductivity, their temperature, and their. So we can decide which one goes to which tank, because we have sensors in line that'll tell us this is the low pH mixture, and not have a person standing there and having to. We actually will know it's coming. We know what tank it's going to go to. When we filter it, we know what tank it's going to go back to, and we can check every time. Tell me the conductivity, the pH, and the temperature to make sure. Now I can also do redox potential to tell me whether it's got oxygen, no oxygen, or peroxide. So I actually have a fairly good panel of what is our cleaning chemistries from sensors, and that'll be in real time.
Okay, great. Well, thank you so much. Thanks
pleasure.
again for taking the time. And John and Roger, thank you so much for joining me.
It's a pleasure, Nick. Thank you.
Great. Well, thank you everybody for joining me. I'm Nick D'Orazio, and see you all next week.